Recording is rolling. It is Tuesday, March 31st. Had a Kahoot for you guys. A bunch of guys are popped in already. It depends on the board behind you here. Tomorrow might be a little bit weird day, especially for your first three classes. There's some testing going on. There might be room relocations. All that information is in Excel page on Google Classroom. Check that out. Tomorrow I will get you guys electromagnetic spectrum and optics quiz. Some content that we covered before spring break, some that we covered yesterday, like review. Some questions you'll see today on this Kahoot. You guys get teammates. I think you guys will be all right. And we're working towards Thursday. How do you guys create this students wheel, dems wheel? Look a little bit more color theory. One thing that came up recently was color mixing, like additive versus subtractive. I have a kind of a cartoon version of a poster of this, but here's actual lamps. Hey guys, what if you have a green flashlight and a red flashlight and a blue flashlight? You shine them all at the same time. What color does that make? Yeah, you're looking at it right there. It's right in the middle, white. Right? Remember yesterday I was talking about colors on your phone screen? Your phone only has 3 colored pixels in it: red, green, and blue. Okay. How do you make yellow again? How do you make yellow? Yeah, with red and green. As long as we're talking about light, right, and additive mixing, which is exactly what you're looking at right there. Some point, I think something about color blindness came up at some point, so I went ahead and printed this out. Now, this looked one way originally on the internet, and then I printed it out, and now it's being projected again, so the colors are still off a little bit. What I'm looking at up there versus actual like in person, as I'm looking at this like face to face, they do look a little bit different. But see if you guys can read these numbers. What's this right here? 12. How about that? 8. 6.
29.
Yeah, 29. Right. This one's pretty tough, just being reprojected. This does say 29. That one, I think even if you're not colorblind, this one's still a little tough.
I get it.
57.
57.
5.
5.
3.
3.
15.
You got 15, I think.
71.
Yeah, I think it's supposed to be a 74. 74?
Oh, yeah.
Yeah, this is a little tricky,
5.
5.
6.
6.
57.
57.
5.
5.
43.
42.
45.
Yeah, 45. There you go. Right. Now, there's different kind of color blindness because you should have 3 different color cones: one for red, one for green, one for blue. If you're deficient in any one of those, right, you may or may not be able to see one worthy. Because if there's one worthy that you can't see, let's throw this one out. Don't worry about this one. Right. Then you might be colorblind. Might want to go check for that. All right, let's do. All right, look at you guys go. Kahoot. Kahoot. Here we go. All right. Compared with the speed of radio waves, the speed of light is.
Oh, wait. I got it wrong.
Sorry about the transparency on that video. Right. Yeah, the same. Right, guys. The speed of all electromagnetic waves, and the speed of all anything without mass, is the speed of light. Now we call it speed of light because that was the first thing to figure out. Goes that speed. Right? But yeah. Okay. So I'll send it. Right. By the way, do you guys remember these mirror puzzles we did? Yeah, yesterday. You guys remember these? Right. If you flip this page over, then all these questions. Okay, that's one we just did. Number 1. Right. Compare this page. Same question. So if you wanted a printout of the questions, then you guys do have those from yesterday. I got extra copies of that. All right, got 109 countries and Boss Baby leading the pack, which is fundamentally different from the others. Fundamentally different. Yeah, sound waves. Do you guys notice that yesterday these other 3 all showed up on the electromagnetic spectrum somewhere? Okay. Like light waves is kind of in the middle of the spectrum. Well, just how it was laid out. Right? That's what your eyes can detect. Anything your eyes can see is somewhere in the visible light part of the spectrum. Because if you stretch out that wavelength longer, they could eventually become which one of these, the red or the blue. How about this radio waves right here? It's radio waves. Right? And if you go the other way, if you increase the frequency, which would be shortening the wavelength, then you could possibly get to gamma ray, would be the other end of the spectrum. Right? Guys, do all these, the red, the blue, and the yellow, do those all travel at the same speed? Yep, all same speed. Okay. Now, and they're also what kind of wave? Are these longitudinal or transverse? Transverse. Right. Now, the guy that doesn't belong on this list is sound waves. That's totally different phenomenon, like fundamentally different. Sound waves require a medium. These are longitudinal. They travel much slower than the speed of light, about 1 million times slower. Yeah. So totally different phenomenon there. All right, got Anna, got her long legs. Netanyahu, boss baby, 109 countries. Difference between a radio wave and a light wave. Yeah, wavelength. Another good option would have been frequency, but not speed, because they all travel the same speed. Right? Guys, remember yesterday we did a calculation. If you tune into an FM station, those wavelengths are approximately 3 meters long, plus or minus a little bit, for FM stations. 109 countries. Dara, Anna, got her long legs. Netanyahu. Compared to speed in air, speed of light in water is what? Yeah, slower. Right, so, and how much it slows down might be called index of refraction. You guys remember index of refraction is what's the ratio of speed of light in a vacuum compared to speed of light inside that material? Right? For water, I think it's like 1.33. So you could say, well, speed of light slows down about 33%, so something kind of like that. All right. Glass is transparent to visible light, but not to Uh, infrared, ultraviolet. I have a UV video queued up for well sometime later today. Right, show you guys. Right, but if your eyes could maybe detect electromagnetic waves in a different part of the spectrum that wasn't just visible light, right, because there is more out there. I bet some animals. You guys think some birds and some maybe some other kinds of animals could see a little bit to the UV or see a little bit to the infrared, right? That maybe humans don't right, really have access to. Right? Okay, so uh, yeah. How about this? Guys, suppose you're gonna plan a day at the beach. I'm going to the beach. I'm gonna be there for like 3 or 4 hours, hang out, have a good time. Do you want to wear sunscreen? Yeah, wear sunscreen. Otherwise, you'll get bad sunburn, and that's really bad for your skin, and lots of reasons to get cancer down the road. Right? How about guys? What if it's really cloudy outside? It's like, well, it's a nice enough day. We'll still go to the beach, right? But it is cloudy. Do you still want to wear sunscreen? Yes. Do you think those UV waves will go right through those clouds? Yes, they will. Even though the visible light doesn't. Right? It can't see the sun or the blue sky, but yeah, those UV go through. Right? How about this? You're going on a road trip. You're gonna drive all the way out to California. Do you have to wear sunscreen inside your car? Do you get a sunburn inside your car? Driving all day, the sun's beaming at you, like my eyes. You got a sunburn? No, because you're behind a pane of what? Glass. Can that UV go through that glass? No, turns out it can't. If you're wearing glasses, do you think you get some UV protection from your eyes? Yeah, turns out you do. Yeah. The same thing with infrared. It doesn't go through glass. Right? So different parts of the spectrum can go through different materials. Visible light can go through glass. Radio waves can go through the ceiling. I got Talia, 109 countries, Daddy Long Legs, Netanyahu, Anna, Clouds. Find out who was listening to me because I just told you the answer. We need to go back to the beach. All right, we're going to the beach. It's gonna be a cloudy day. You still want to wear sunscreen? Yes, you do, because you still get a sunburn even on a cloudy day. If you're out for a long time. Yeah. Boss baby, Netanyahu, Talia, got long legs, Anna. I don't know why it's cut off at the bottom. Sorry about that. All right. Electron vibrates 1,000 times per second. What does that mean? Vibrates 1,000 times per second. What is that? Ah, there you go. Frequency 1,000 hertz. Ah. And what would the time period be?
Such things.
Like
some
one
fraction.
Yeah, there you go. One millisecond. Yeah, 1/1,000 seconds. What would the speed be? Huh? Yeah, speed of light. 3 × 10⁸ meters per second. Right? Could you apply speed equals wavelength times frequency? And you know the frequency. You know the speed of light. You could solve for the wavelength. You could. Speed equals wavelength times frequency. You can do that. Little equation. All right, net Yahoo, boss baby, Talia, daddy long legs, Adam. Ooh, how far is a light second? Right, because if you look at that number, so translation here. What's kilo? Kilo is a factor of a what? 1,000. So hey, could that be 3 × 10⁸ meters? Oh, if that happens in 1 second, you'd have to travel at 3 × 10⁸ meters per second to travel that distance. Guys, if you ever see anything like light second, light years, that's referring to a distance. It's how far does light travel in that interval of time. Right? So for 1 second, it'd be 3 × 10⁸ meters. Right? How about these other ones? We're about 1.5 seconds away from the moon. Okay, so if you're communicating with astronauts on the moon, there's going to be a communication delay. It's going to be a little gap. Okay? It takes about 8 minutes for light to get from sun to Earth. Here's the nearest star to us besides our own sun. Okay? Is 4.2 light years. So if you traveled at the speed of light for 4 years, it would take to get there. Not the scale, of course. All right, 109 country, net Yahoo, daddy long legs, Talia, Anna. Distance light travels in a year is called 1 light year. True. Yeah. Ooh, colors on a TV screen. Yeah, color addition. Right. So like the more colors you add in, the closer it gets to white light. Right? That's something that Isaac Newton figured out. Right? Oh, guys, if you put all the colors together with color addition, it makes white light. Right? Like if you're seeing this white on the screen right here, you guys see this white right here? Is that because the red, green, and the blue are all shining? Yeah, sure is. Oh, here, do I still have... Oh, I still got that. Okay. How do you make black? How do you make black on your phone screen? Yeah, just none of the pixels are turned on at all. Yeah, you turn your phone off, now you have a black screen. Yeah. Of course, it's different with paints or coloring. Yeah. I wonder if that's a question coming up. Here we go. Printed photograph. You print a photograph from your color printer. Going on there. Yeah, it's the exact opposite. So this is color subtraction. This is how ink works. Okay, so you have 3 color inks in your color printer. So guys, suppose you run yellow ink and blue ink at the same time. Okay, now yellow ink reflects everything except for yellow, but there's also these other colors in there too, right? Like if I look at the color addition side, I know yellow also involves some red and some green. Okay? I see some red, some green. Okay? So it allows red and it allows green. The color yellow does. The pigment yellow. Okay? But if you also mix blue, now it subtracts out the red. You can think of it that way. Hence color subtraction. Right. So if you have yellow ink and blue ink, that makes what color? Yeah, green. So that's how you get green from a color printer. But that's color subtraction. It has nothing to do with on your phone screen or anything like that. Okay. All right. Oh yeah. When blue and yellow paints are mixed. Oh. Okay. Yeah, so, okay, since we're talking about paints, pigments, color subtraction, all colors are absorbed except for green. Absorbed except for green. Okay. And of course, if you mix a bunch of different paint colors, the yellow and the cyan and the magenta, yeah, that'll bring you back to black there. How about yeah, I meant to say cyan before instead of blue for the ink color. What else I want to ask about this? Guys, what does this right here mean? What does complementary mean?
Or,
Yeah, across from each other on the color wheel, like the opposite color. And actually, if you look at both of these color wheels, are they the same pair of complementary colors? Like on the addition, it looks like red is opposite of cyan. And on the subtraction, hey, red is opposite of cyan. Hey, how about yellow is opposite of this deep blue? Yellow is opposite of this deep blue. Hey, complementary. There you go, complementary colors. All right, I got Boss Baby, Anna, Daddy Long Legs, 109 Countries, Talia. Ooh. Three primary colors for additive color mixing. There it is, red, green, blue, which is those right there. Got a red lamp, green lamp, blue lamp. That's all you need to create all the colors with lamps. Yeah. It is difficult to tell a roadway from a car on a rainy night because the roads are. Oh, there you go. Why? Ooh, got one winner. Diffuse when dry becomes a mirror when wet. Because anything that's diffused, which is most things in this room, if you look around, it doesn't matter where you position the other objects, unless you're a block and light or something. Right? Like this white wall will always be white. Right? You shine a light on it, looks white from any angle. Right? But it's not really true with the mirror. With the mirror, you get this reflection. So like wall of reflection, right? And light will travel in straight lines and bounce off in straight lines. Okay? And so that goes back to this picture right here. Okay? So this road used to be diffused. It was always just like asphalt gray or whatever, right? Regardless of whatever. Right? But if it's wet, now it turns into a mirror. Now it turns, right? You see that? Right? You get that spectral reflection, right? Instead of diffuse reflection. Dara, Talia, Anna, Daddy Long Legs, 109 countries.
I could subtract Benjamin at Yahoo.
Refraction. So that might be the fancy physics term for bending. But when would waves bend? Right? When they change speed. Anytime a wave changes speed, it's going to want to bend like that. Change speed. Um, ooh, guys, can you have refraction with sound waves? Can you have? Yeah, you can. Okay, I think it's kind of junk. Yeah. So when a wave changes speed, you know what? Here, let me find a bonus video for you guys. You got a Paul Hewitt somewhere in here. Is it? I think it's this one.
Rest assured, sound will travel a little faster on a warm day than a cold day. And let me give you some evidence of that. It's something that occurred to me when I was a kid. I couldn't figure it out. And later on, when I got into physics, boom, the answer to my question came. When I was a kid, I used to be a Boy Scout. And we used to go camping up at Camp 9 in Saugus, Massachusetts. And we'd camp on one side of the lake. This is a lake. And there'd be another scout troop over here. And we'd have our tent set up here. And we'd tent out here, you know, there's our troop here. Here's that troop over here. They've got their tents. Okay. In the daytime, you could yell over to these guys, hey, you guys, how you doing? And they say, speak a little louder, I can't hear you. How you doing? Fine, how you doing? Oh, okay. How's it going? Oh, you know, these heavy conversations you have, yeah? But it turns out we could just barely hear each other. But at nighttime, you could hear these guys whispering in the tents. You could hear them so clearly. I can remember that. And I wonder, wow, at nighttime I can hear those guys. How come I can hear them so good at nighttime? And daytime I can't. And I didn't know the answer to that. And it took me a long time to find the answer to that. Has anyone ever experienced something like that? It's not all the time true, but under special conditions, sometimes you can hear a lot clearer over a long distance than other times. Let me tell you what happened, okay? It turns out that over here, let's suppose over here, someone's, hello, how are you? And we get sound waves coming off like this. And the sound keeps going. Now, it turns out the direction of sound will always be at right angles to the waves. So for example, like this, it's, and up here it's right angle, right angle, right angle. See that? So when all the air has the same temperature, then the sound will travel at equal speeds in all directions and form all these circles, yeah? But how about in the case where maybe at nighttime, it's relatively cool above the water and relatively warm up above, a so-called temperature inversion. When that happens, how about this wave? Will this wave get to here or will it be further along? In the warm air, it will get to here. In the cold air, it would get to here. And up here, maybe up to here. So you know what's going to happen to the wave, gang? The wave is going to be bent more like that. And when it gets over here like this. Now, my rays being perpendicular up here. Ooh, look at that. See that? Okay. So what you're doing is you're getting more energy in the air at nighttime than you are in the day because the sound is being bent. The waves are being bent. We don't say waves bend because one part's going faster than another. We have a name for that. What's it called, gang? Refraction.
There you go. When you see a wet spot mirage on the road, you're most likely seeing an image of. Ooh, you guys seen that? Maybe if it's a really hot day outside. Looks like water, but you drive up to it, it's not really water. Okay. Yeah, so the idea is it's actually really similar explanation the way it was just shown with the camping and the tents and the sound waves being refracted. Right. So now we're back to light. Okay. If it's a really hot day outside, you might see if it's really hot. You think right above the surface of the asphalt pavement, super hot, super hot. Okay. And when that light ray comes in a straight line and hits that pocket of really hot air right above the asphalt, it bends. And when it bends, then now it's going to bend into, well, the windshield of the next car, which maybe you're driving there, and then you see a portion of the sky. There you go. So refraction. Refraction. A person standing waist deep in a swimming pool appears to have short legs because of refraction. There you go. Refraction. Oh, we got Really Spitzer, Daddy Longlegs, Anna, Talia, 109 countries. Ooh, who remembers this one? Yeah. Okay. And so I got a poster on that. I gave you guys some notes on that the other day. Yeah, if you're 6 feet tall, you have a 3-foot mirror. If you position it just right, you can see your entire reflection. Really Spitzer, Daddy Long Legs, Anna, Talia, 109 countries. Look at yourself in a pocket mirror and then hold the mirror further away. Yeah, say amount of yourself. I had one that's passed around class. You guys got to try that. Yeah. And so those last two questions go hand in hand. Really Spitzer, Daddy Long Legs, Anna, 109 countries, Talia. Reason lines look wavy, bottom of swimming pool.
Must just be.
Yeah, refraction, even surface or uneven surface. Water. Refraction. All refracting lenses, like that magnifying glass. Or that telescope right there. Ah. Yeah, slower speed inside the lens. Okay, so the process is if light slows down, it's going to refract. How much it refracts depends on that index of refraction, how much it slows down. Okay. You guys do Snell's law. You guys remember Snell's law? N1 sine theta 1 equals N2 sine theta 2? You guys remember Snell's law of that? Okay. And then depending on what's the focal length of that lens, tell you how much it's going to magnify. There you go.
Yes. Yes.
If light didn't slow down, here, guys, how about this? I think I remember the last question too. Great. Hey guys, if light did not slow down at all, would this magnifying glass even magnify at all?
No.
No, because there would be no refraction. Right? It would be like it would be like there was no glass here at all, and I was just like holding an empty ring, saying, ha ha, ha ha. It would do nothing at all. Right? What about this? I think the last question is if you take this under the water in a pool. Right, you guys ready yet? Right, let's go to a pool. Let's jump under the water. Right, and now I'm magnifying. Like, yes, the bottom of the pool. Yeah. Guys, does this work better in water or worse in water? What do you think?
Worst side.
I'll give you guys a hint. I'll give you guys a hint. How to think of it. I think it's the next question, so I don't want to give it away exactly, but I'll tell you how to think about it, how to frame it. Guys, what's the index of refraction of perfect vacuum? Yeah, it'd be exactly 1. 1.00000. Okay. How about index of refraction of air? Pretty close to what?
1.
Yeah, pretty close to 1. It's like 1.0. I think it's 1.008, I think. I could look that up. Okay. We'll just call it 1. Okay. Does anybody know index of refraction of water about? It's like 1.33. I think it's 1.333. Okay, something like that. Okay. And then how about glass? Now there's different kind of glass, so there could be maybe a little range of answers to this. Okay. Well, what do you think? Suppose if you had to guess for this, it'd be pretty close to what? It's usually like 1.5. Okay. Okay, like 1.5. Okay. Did I tell you guys the other day? Show of hands. How many of you guys are taking forensic science? Who's taking forensic science? Ready? Okay. A few of you guys. Did you guys learn about this refraction method where so let's say you get a sample of glass from a crime scene, like that found a sample of glass. Maybe there's like a car crash or something. Okay. But I don't know what car it came from. So I take this back to the lab, and I know there's different kind of glass with different indices of refraction. Okay. So I'll I take this little piece of glass, this little shard of glass, and I'll drop it in this oil. I forget what kind of oil, whatever. Okay. But if I change the temperature of this oil, then it changes the index of refraction of the oil. Okay. And suppose this glass, the index of refraction ends up being like 1.497. I'm just making something up. Okay. Okay. If I can make this oil right here also index of refraction of 1.497, then guess what it looks like from the outside? Completely invisible. Completely invisible. You don't even know there's glass shard in there. Like you can't even see it. And that's how you know. Like, aha, now I know the index of refraction of that glass. Ah, see like that? Okay. All right, so now we're gonna go back to this pool. Okay. This magnifying glass right now is able to magnify because the index of refraction of the glass is 1.5 versus air is 1.0. That's a difference, isn't it? Now what if I take this underwater? There's still a difference. Let's see if you guys follow that whole. I've been trying to lead you guys into something here. All right, you guys ready? You guys ready for the win? This is for the win. Who's gonna win the whole Kahoot? Will it be really Spencer? Will it be Daddy Longlegs? Will it be Anna? Will it be 109 countries? Seems unfair. Will it be Talia? Who will win? Magnifying glass underwater will magnify how compared to air. Yeah, not as much, not as well. It doesn't work as well. Okay, let me back this up with Snell's law. You guys remember Snell's law? Okay. Goes n1 sine theta 1 equals n2 sine theta 2. I like that. Oh, index of refraction, of course, is what the speed of light in the vacuum compares to speed of light inside this particular material. So for vacuum, of course, it's 1. Okay. Okay. Now, guys, now instead of going from air to glass to air, okay, which is like 1 to 1.5 to 1, something like that. Okay. Now we're going from water to glass to water. You guys see that difference in index of refraction is not as much? Okay. In fact, if these indices of refraction were exactly identical, now we're back to this forensic science experiment where there's no refraction at all. And light just travels in a straight line and you have a completely invisible glass. Okay. Okay. Yeah, so the closer together these indices of refraction, the less the refraction. Therefore, the less the magnification, and your magnifying glass does not work nearly as well. Sure doesn't. Let's find out who won Kahoot. Oh, with the bronze, Anna, silver, Talia, and the gold, 109 countries.